everyone. It's great to be here in sunny Santa Clara. Thank you so much for having us. Today we're going to talk about the time that it wasn't DNS. So I'm Elijah Andrews, and this is Hemanth. We've already had introductions, so we're not going to spend too much time on this slide. We're here talking on behalf of Datadog, and this isn't to talk about Datadog, the tool. We have a great booth in the exhibition hall if you want to go check it out. We're an observability platform if you're not familiar with us. I'm not going to go over all these figures here, but we integrate with all the things and give you a way to see what's happening in your production systems. We're also very big Kubernetes users. So here are a bunch of numbers about like the sort of scale that we're operating here. And in particular, the one that's interesting to us is that we run hundreds of Kubernetes clusters, and some of them are quite large. Sort of as like a warning for this presentation, there's a lot of Kubernetes stuff in here. I'm sure many of you people do use Kubernetes. I'm sure many people also don't. But just to make sure that we're all on the same page and you understand like all these nouns that we're using, I just want to define like a few of the terms that are going to come up in the presentation. So in Kubernetes, you schedule pods on nodes, and pods are a collection of containers that are managed by application teams. Each pod has a unique IP address, and there's a bunch of networking magic that has to happen between host networking, pod networking, and AWS, which is our cloud provider. And we use a thing called Cilium in order to manage all that stuff. That's done through our container network interface. All right, so now we're actually going to get into the talk. Here's how it started. So we have a service at Datadog. It's called the metric service. It's this one that's highlighted in red in the middle. And what the service does is it serves time series data to a bunch of other components at Datadog. So Datadog, one of Datadog's products is a time series data monitoring platform. And when you go to Datadog and you look at a graph and it has a bunch of time series data on it, that data is served by the metric service via the web app. And we also have an alerting platform, so you can set thresholds on metrics and say, like, if this metric reaches this threshold, page me, wake me up, and I know I need to fix something. And behind the scenes, the metric service is really just gluing together time series data from a bunch of other places. So first, it hits an index service that tells it where it needs to go query the actual time series data, and then it hits a storage layer. And it grabs all that data, and it glues it together and returns it to the dependencies. And so the owners of the metric service came to us, and they said, we're having this really weird problem. So every time that we do a rolling restart of our service, we see a bunch of errors for a long time afterwards. And so here you can see the error rate that they were seeing. So this like purple line that's going up here is showing that there are a lot of server-side errors that are happening. The client side wasn't seeing a ton of errors here because they were actually set to do retries. But what they did notice, even on the client side, was that the latency had gone up a lot, and this was causing problems for their systems. And so we did what you always do when you have a problem in infrastructure. You check your logs, and your logs tell you that it's DNS, and that makes sense because it's always DNS. And it really looked like it was going to be a DNS problem. It had to be DNS, right? Let's dive into DNS. So here's the metric service again. So the DNS errors that we were seeing here were errors that the metric service was seeing when it was trying to talk to its dependencies. So we use DNS for service discovery at Datadog. And so this is manifesting itself as client errors when the web app and the alerting engine talk to the metric service. So here's an overview of our DNS setup. So this is somewhat conventional like Kubernetes DNS setup. We have the metric service, and then on the same host, we have a local caching and forwarding DNS resolver, which is called node local DNS. And when the metric service makes a DNS request, it forwards it to node local DNS, which looks in its cache. And if its cache doesn't have it, then it queries something called cluster DNS, which is just a Kubernetes cluster-wide DNS deployment that, again, does caching, and it's authoritative for things within the cluster. But if you remember back on the Kubernetes slide, I said that we run hundreds of Kubernetes clusters. And Kubernetes doesn't really do anything for cross-cluster discovery for you. So sometimes, or very often, actually, we have to go to an external DNS provider. And in this case, we're using Ret53, so that's AWS's managed DNS solution. And so when we looked at the logs, the metric service was emitting DNS errors. And they were actually coming from node local DNS itself. This is quite strange. We actually thought that the issue was going to be coming from like somewhere where a network request was happening. Usually things that happen on the same instance like work properly when you don't actually have to go over the network. But we dove in. And so when we looked at a bunch of metrics, and we noticed that node local DNS was actually running out of memory, and it was being out of memory killed or killed by our container runtime. And this was happening during rollouts. And this was really quite strange, because we thought that this could never happen. And it should never happen. And the reason it should never happen is because we have a setting in node local DNS called max concurrent, and it's set to 1,000. And this tells it that it can only serve 1,000 DNS requests at a time. And we do this because the amount of memory that this process consumes is proportional to the amount of requests that it's serving. And we looked at the metric for the max concurrent request reject rate, and it was being hit. So we were like rejecting requests, but this just suggested to us that the sizing for our DNS process was wrong. And so we were previously giving this thing 64 megabytes of memory, and we decided to just quadruple the amount of memory that we were giving it. So we went up to 256 megabytes. And so our memory consumption sort of stabilized at like 128 megabytes. We weren't running out of memory anymore, but we were still hitting the max current request limit, and we were still seeing the same problem. So this actually wasn't the issue. At this point, we were quite confused, and we started doing a bunch of math, and actually like none of it really added up. So we set max concurrent to 1,000, and if we budget like 5 milliseconds for node local DNS to make a DNS query, which is quite generous because a lot of things are hitting caches and like or going over like local networks, and so like that's a ton of time. Node local DNS anyway should be able to do like hundreds of thousands of requests per second, but we're hitting max concurrent at like a few hundred requests per second. So that's quite strange. And we looked at more graphs, and we realized that the error was actually happening in the node local DNS forwarding component. So if you remember that DNS diagram from before, node local DNS, if it can't answer a query, forwards to cluster DNS over TCP. And what was happening was the forwarding component of node local DNS was saying, I actually can't contact the upstream resolver, so I'm going to return an error. And the way that works is that it actually forms TCP connections to the upstream resolver, and it reuses those connections. And normally this works fine for us. And after every 10 seconds, those connections expire. But what was happening was, for some reason, it was actually unable to connect to the upstream resolver. And this made a bit more sense, at least in our math. So we looked at what the timeout was for node local DNS to contact the upstream resolver, and we were just using the default value there, which was 5 seconds. And so this meant that incoming queries would occupy a query slot for about 5 seconds as I was trying to establish that connection, and then I couldn't establish the connection in timeout. But this means that we would hit max concurrent with only about 200 requests per second, which like matched what we were seeing. And at this point, we started thinking that we were actually seeing a networking issue. So we looked at the expected network throughput that we could get on the instances that we were running here. So we were using M5 4x larges. This is an AWS EC2 instance type, if you're not familiar with it. And this thing says that we can burst up to 10 gigs per second, and we can sustain 5 gigs per second. And we looked at the throughput graphs, and everything looked fine, so we weren't hitting saturation, at least according to this graph. But we were still seeing signs of network saturation. So in particular, we were seeing TCP retransmits when the metric service node was trying to make connections outbound. And this still suggests that we are seeing some sort of packet loss somewhere in our network. And so one thing that we started thinking that we were seeing here at this point was maybe there was microbursting. So this is like the problem here that might have been happening is that we have really short-lived spikes that are happening in our network. And when you have reporting, like there's some aggregation that's happening. It has to do averaging. Like the agent that's reporting these metrics is reporting data every 15 seconds. And also there's like a finite number of points on this graph that's like fewer than like the number of data points that we actually have. So there's some sort of like averaging happening. And maybe that's eating our data. We actually see this type of problem a lot. And when we see this type of problem, what we usually do is look at measurements that are not subject to averaging. And in particular with networking, you can often get metrics from the network driver, which just count events that happen. And these don't count, these are not subject to averaging. And luckily, a few weeks before we started having this incident, we added support for elastic network adapter metrics in Datadog. So if you're not familiar with it, the elastic network adapter is, this is like a networking component that runs in the hypervisor part of an AWS instance. So this is outside of our VMs. It's like on like the host machine, and it's in Amazon land. But the thing that's interesting that they added is that if you run ethtool-s, you can actually get network driver metrics from this thing. And we added support for that where we could report them in Datadog. And so I'm going to pass this off to Hemanth, but just to summarize where we are so far. So we are seeing DNS errors in the metric service on rollout, and node local DNS was telling us that it could not establish connections to its upstream resolver, which suggested some sort of networking issue.
So this brings us to chapter 2, which is AWS Networking, where we'll look into what's happening on the network card of the instance. So as Elijah mentioned, we were thinking that our throughput metric might be misleading us because our throughput metric might be averaging out the microbursts that we are seeing. So in order to verify this hypothesis, we wanted to look at the new ENA metrics that we had available. So, and once we started looking at those metrics, one of the metric that really popped out for us was this metric called ENA bandwidth exceeded. And if you look at this graph closely, it looks like we're almost always going over the metric, going over the bandwidth limit on the node. And it turns out that we are actually saturating this instance. And maybe this is normal TCP behavior, right? Because TCP is self-regulating. But what's really worrying is that this did not really correlate with our rollout window, as you can see from the rest of the graphs. And at this point, we had no idea what we were really looking for, but we continued looking. And totally by chance, we discovered another metric called ENA conntrack exceeded. And we discovered this metric only because it was completely correlated with our rollout window. And at this point, we were running tens of thousands of instances on AWS, but we never had to deal with conntrack on AWS. So we were curious what this metric really was. So we looked at the documentation. And Amazon told us that in order to implement security groups, which are stateful firewalls, Amazon needs to maintain entries in the conntrack table on the hypervisor. And what this metric really was telling us is that during the rollout of our metric service, we are saturating this connection tracking table. So the first thing we really did was to try out better instances, and we switched from the instance we were using at that point in time, M5 4x large, to network optimized instances, which are M5 and 4x large. And as you can see from the graphs and the purple and gray line, things started looking much better, and we weren't exceeding our bandwidth limit as much. But unfortunately, the conntrack exceeded metric was unaffected by this, and our DNS response time was still spiking up during rollout windows. But what about bigger instances, right? So we switched from M5 4x large to M5 8x large, which are twice as big, and the issue totally went away. And as you can see, the TCP retransmits completely went away. We were not saturating the conntrack table, and the DNS response time was unimpacted as well. But what this really meant was that our metric service would now become twice as expensive, which is a bit of a hard sell with our metrics team. So we really had to get to the bottom of why this was happening. So, and at this point, we couldn't find any public numbers on what the max size for this conntrack table was. So we reached out to AWS and asked them. What Amazon told us was that don't really worry about it. You should be able to track hundreds and thousands of flows. It has never really been an issue. But they also told us that, yes, bigger instances have bigger conntrack tables, and that made sense based on our tests. So we went back to our hosts, and we looked at the Linux conntrack, because Linux also has its own connection tracking. And when we graphed the metric, what we realized is that in our stable state, we have around 13,000 connections. And during rollouts, we were spiking up to 60,000. This is high, but it's still an order of magnitude lower than what Amazon was reporting for us. So at this point, we had no idea how to proceed. So we wanted to look at the underlying TCP connections. So we wanted to look at VPC flow logs. And VPC flow logs are similar to Cisco's NetFlow logs. And for every TCP connection, you would have two entries, one for egress and one for ingress. And of course, these are very huge in volume. So we used Amazon Athena to filter these logs. And at this point, we know that during the rollout window, our node local DNS is unable to talk to its upstream, which is cluster DNS. So we wanted to look at the egress flows. So we gathered all the VPC flow logs from one of our metric service node and grouped them by source IP. And as you can see, the line on the left, which is red in color, is flows from the old IP, and the yellow line is the flows from the new IP. And what you can see from this graph is just before the old IP went away, we're seeing a huge spike in flows, and that's interesting. And when we looked at the corresponding ingress flows, it looked even more weird because now we have a second spike here that does not really correlate with our egress flows. And generally, every ingress flow should have its corresponding egress flow, but that's clearly not the case here. And in order to understand why there is this discrepancy, we then decided to aggregate these flows with TCP flags instead. So if you look at this graph closely, the blue line here indicates connections that are already established. So these are the long and established connections. And that makes sense because these connections don't really have any TCP flag set on them. And the red line indicates connections that are terminating. This also makes sense because we are in the rollout window and the old pods are going away. And as the old pods are going away, the connections are terminating, so they're sending FIN packets. And the most interesting part here is the SYN packets. And you can see that what this really means is that somebody has been aggressively trying to reconnect with our metrics service. And there are almost 130 connections under 90 seconds, which is extremely high. And when we looked at the corresponding egress flows by TCP flags as well, we can see that the first spike has a corresponding TCP reset, but the second spike does not have anything. So we didn't understand why there was this discrepancy. So it turns out that our metric service was actually a GRPC server, which was implementing graceful termination with a timeout of 10 seconds. And during this 10-second window, the server would stop accepting any new connections, and any new incoming connection would get a TCP reset. And after this 10 seconds, the pod is deleted, and the IP is not bound by anything. And that kind of explains why we see the resets only for this first spike and not for the second spike. So because we had VPC flow logs, we had source IPs available on every flow log. So we also looked at where these TCP SYN packets were coming from. And we realized that this was actually coming from our alerting engine itself. And when we looked at the conntrack on these alerting engine nodes, it kind of confirmed that for us. And this conntrack graph actually correlates with what Amazon was telling us. So to summarize what we understand so far, during the rollout of our metric service, we're seeing DNS errors. And in that window, node local DNS on the metric service node is unable to talk to its upstream, which is cluster DNS. And the conntrack on those, it seems like we are saturating the conntrack on AWS hypervisor. And our alerting engine has been SYN flooding us during rollouts. But what we still don't understand is why the conntrack that is reported by Amazon's hypervisor and the conntrack on the metric service node is very different. And in order to understand that, we need to get to the next chapter, which is node networking. As Elijah mentioned, we use Cilium for our pod and node networking. And Cilium primarily consists of two components, the Cilium operator and the Cilium agent. And Cilium operator is really the only component that can interact with the cloud provider APIs. And this is really helpful because this allows us to centralize all the API calls that we're making to the cloud providers so that we can have better rate limiting and things like that. And the operator does things like creating new interfaces on the node, allocating IP addresses or prefixes to these interfaces. And the operator always makes sure that there are enough IPs available on the node for allocation. And the Cilium agent and the Cilium operator talk to each other via a custom resource definition in Kubernetes. And the IP pool information is exchanged via this object. So the Cilium agent picks up the data that is available on the CRD object and can allocate them to the pods that are being scheduled on the node. And in Kubernetes, every pod gets its own network namespace, and Cilium creates a v-eth pair for every pod so that this pod's network namespace can talk to the host network namespace. And at Datadog, we also have dedicated interfaces for pods. So we have at least two interfaces on every node, ENS5, which is the host's default interface, and ENS6 and above, which is the pod's interface. And Cilium also needs to make sure that the packets can go in and out of these pods. So for ingress, Cilium installs route table entries so that every time we see a packet with the following destination address, send the traffic to this corresponding v-eth pair. And egress routing is implemented using source routing. And Cilium installs a few IP rules in order to implement that. Basically, it says that when you see a packet with the following source address, send the traffic, look up the following route table. And in that route table, there's an entry that sends the traffic through ENS6. So with that understanding, now let's look at the stable state. So in our stable state, an alerting node is trying to talk to our metric service node, and it does that by sending a SYN packet. And when the SYN packet is sent, you can see that the conntrack is consistent in all the 3 components that we are interested in, which is the alerting node's conntrack, the hypervisor conntrack on the metric service node, and the Linux conntrack on the metric service node. And all of these entries are currently in SYN receive state. And when the metric service node responds back with a SYN ACK, all of these connections are now transitioned to an established state. But what really happens when we send traffic to an IP that was deleted, right? So at this point, Cilium has already garbage collected all the routing information and the IP rules information. And the clients would continue to try and send packets to this IP address because it takes some time for our service discovery to propagate this information all the way back to the clients. And as far as the VPC fabric is concerned, the IP address is still attached to this interface. So any packet that is sent to this particular IP address, VPC fabric will still send that to the same node. So the packets arrive on this ENS6 interface on the metric service node, but once they arrive, where do they go? Right? Because we don't have any corresponding routing information for it. So we didn't understand that as well, so we wanted to try and simulate it. So we went to a different node and tried to connect to one of our metric service node and ran TCP dump on one of the metric service node. And we saw that the SYN packet is actually received on this node, but it never got any response back. And when we have questions like this, we can actually ask the kernel, if you get a packet with the following source and destination IP address incoming on an interface called ENS6, what would you do with it? And we saw an error that looked like this. And generally, errors like this could mean that we're hitting the kernel's reverse path filtering. And one of the important features of reverse path filtering is that we would see Martian packet logs when you look up the kernel logs. And when we pulled out our kernel logs, we could see that we were actually hitting the reverse path filtering. And reverse path filtering is basically a security feature that is in place to prevent IP spoofing. And reverse path filtering has 2 primary modes, strict mode and loose mode. In strict mode, what strict mode basically says is that drop the packet if the return path uses a different interface. And in loose mode, only drop the packet if there is absolutely no route out of the host. So what this means is that in loose mode, the return path can use any of the interfaces that are available on the host and not just the interface that it came in. So now when we go back to our metric service node, now we can reason about it a little bit better, because when an alerting node sends a SYN packet, the conntrack is updated on the alerting node's conntrack table and the hypervisor's conntrack table, but it's never updated on the node's Linux conntrack table because we are hitting reverse path filtering and the packet is being dropped right away. And that kind of explains why we see this inconsistency between what's reported by Amazon and what we're seeing on the host itself. But what's still confusing for us is that we actually configured reverse path filtering in loose mode, which is actually the default in most of the distributions. And we have a default route through ENS5, so all packets should be able to leave the host through ENS5. So technically, we should never be hitting reverse path filtering at all. And we had absolutely no idea why this was happening. So we had to look at the ultimate source of truth, which is the kernel source code. So we pulled out the reverse path filtering source code. And if you take a look, it's actually not that complicated, because we know that we're hitting this error called cross-device link, which is defined by this macro called exdev. And in order to get to exdev, you need to go through this label called ERPF. And in order to get to ERPF, we need to go through last resort. And now things started to get interesting because there is this variable called noadder, which is being set earlier in the function. If a packet is received on an interface that does not have an IP address set on it, the packet would be dropped because it hits reverse path filtering. And turns out that this was the case in our Cilium setup. And Cilium never really allocated an IP address to the pod secondary interface because we don't really actually need it. So we wanted to try it out, and we went back to our experiment and allocated a random IP address to our pod secondary interface. And we reran the same command. And lo and behold, kernel told us that the packet would now leave the host through ENS5, and it would not hit reverse path filtering. And another thing we noticed is that the recent versions of Cilium noticed this and actually started allocating IP address. And if we had an IP address allocated to our secondary interface, the packet would still be dropped because it would go out through the VPC fabric and it would be eventually dropped. But our conntrack would have been consistent across the board, and we would have figured out the issue much sooner. And after we noticed this, we also contributed a small pull request to Cilium in order to add an additional unreachable route for an IP address that has been deleted, so that the clients can get early feedback in the form of an ICMP error so that they can take the necessary actions. So to summarize what we understand so far, during the rollout of our metric service, we are seeing DNS errors. And during this window, node local DNS is unable to talk to its upstream, which is cluster DNS. And it looks like we've been saturating the conntrack on the AWS hypervisor. And our own alerting engine has been flooding us during metric service rollout. And the conntrack is not really consistent between what Amazon is reporting on their hypervisor and what we are seeing on the host, because we're hitting a reverse path filtering. And we're hitting reverse path filtering because of an edge case in the kernel. But what we still don't understand is why we are seeing so many SYN packets being sent during rollouts.
And in order to answer that question, we need to look at the way that our RPCs are set up. And so we broke this question down into two sub-questions. So the first one was, why were we sending requests for so long? We noticed that we had this wide window that was like 60 or 90 seconds long where we were sending SYNs. And then also, why did it have like these huge spikes in it? And to answer these questions, we need to look at different parts of the RPC setup. So to answer the first one, we need to look at the propagation delay in the service discovery component of our system. And to answer the second one, we need to look at the way that we use GRPC at Datadog. So for the service discovery component, just remember that we use DNS for service discovery, and that has to hit RET53, which is our external DNS provider. And then for the query component, we use gRPC at Datadog. And one important thing about the way that we use this is that we actually do what's called client-side load balancing. So this means that we have a single domain name that returns a bunch of IPs that are metric service pod IPs. And then the clients make local decisions to decide which IP it needs to hit. And we try to do like some load balancing there. There's no address translation here, or there's no like load balancer in the middle. All right, so first let's look at the DNS propagation time during rollout. So this is the way that this works, that our service discovery is set up here. So we have something called external DNS, and this is a Kubernetes controller, but it's actually just a process that runs, and it looks at the Kubernetes API server, and it looks for events. It looks for pods coming online and offline, and it just grabs the IP of that new pod or that old pod, and then it updates the DNS provider so that it knows that that update happened. And so here, external DNS calls that update. It updates RET53, and then alerting engine queries RET53 over DNS. And here, we looked into all of the stages where we could have propagation delay here to try to get an estimate for how long it would take. So the first step here is on the right. It's external DNS. It has to pick up the change and realize that the metric service pod was deleted. So what happens here is we send a termination signal to a pod, which triggers a gRPC graceful stop with a 10-second timeout. And during that time, metric service starts rejecting new connections, and it waits for old requests to finish. One interesting sort of bug or feature that we found in the version of external DNS that we were using here is that we actually didn't trigger the deregistration event in external DNS when the pod received the termination signal. We actually only did it when the pod went away entirely. So that always took 10 seconds. That was something that we changed after this incident. And then in external DNS, we have a sync loop where it runs every 15 seconds. and updates a record in Rep 53 with a TTL of 15 seconds. And sort of something that's interesting here is this is sort of, it's a trade-off that we encounter a lot when we're using cloud provider APIs. We want the sync loop to run really frequently so that we get updates quickly, but also if we run it too frequently, we'll hit API limits, and then our stuff will completely stop working. And so both like our sync loop time and the TTL time was this middle ground that we tried to find where we could have like good availability, but also not just like completely blow through our rate limits. Anyway, so there's the TTL of 15 seconds on the Rep 53 record, and that's also can be cached in the no local DNS resolver. And the last thing that we needed to figure out was how often does the alerting engine pod actually try to re-resolve the DNS record? And we found this is actually bound by a GRPC setting, which is called min time between resolutions, which is set to 30 seconds. And so what this says is that you should always wait at least 30 seconds before trying to re-resolve a DNS record when you encounter connection errors. And we just used the default value here, which was 30 seconds. And this is kind of interesting, actually, because it says that all of the clients will receive updates in sort of like quantized windows of like 30 seconds, sometimes 30 seconds, but usually 60 seconds, and also sometimes 90 seconds. And it actually explained a lot of the weirdness that we were seeing when we would look at graphs like this, and we would see that all the events were always happening in like 30-second increments, and we were super confused. But yeah, if we look at this graph here, and we're just looking at how wide the amount of time that we're sending the SYNs is, this sort of matches what we found there. After like 30 seconds, we have our first batch, and then after 90 seconds, we've completely switched over to the new IP, and everything is good. So that explains the width of that graph, but it doesn't explain the spikes. And to explain the spikes, it's a bit more involved. We have to go into the history of the way that we used gRPC at Datadog. And we started using gRPC in 2018. Before that, we used a homegrown RPC protocol. And for some context, one thing that we were doing back then was we would actually write really thick clients. And these clients would be aware of the way that their dependencies were sharded. We would have sharding on the server, and the clients would actually download partition tables. And when a request came in, they would like do a bunch of computation to figure out what partition they should hit. And they would actually do like string concatenation to form DNS names that corresponded to the correct partitions. And since we were doing all that work in our applications anyway, we were like, hey, why don't we just throw DNS resolution in there too? And it can manage like the name to IP state. And so we would actually just pass the IP address to gRPC and say, you should connect to this server, and everything works properly, sort of. If you've used gRPC before, you know this is probably like a bit of an unconventional way to use it, because gRPC actually has a bunch of code in itself where it can re-resolve domain names, and it's pretty good at like trying to rediscover when dependencies change. And so about 6 months before we had this incident, we actually decided that we were going to change the way that we use gRPC, and instead of having all of our domain name resolution code in applications, we were just going to put it in gRPC itself. And this was great. We made that change, but when we did it, we noticed that our servers only started connecting to one of the upstreams instead of multiple ones, because we were just passing it a single domain name. And the default load balancing strategy in gRPC is something called pick first. And in pick first load balancing, it just tries to connect to one IP. It doesn't try to connect to all of them. It's a bit of a strange default value. But we thought, great, like we'll just switch it to another load balancing policy that's built into gRPC itself, which is called round robin. And that says you should try to connect to all the IPs that are returned by a domain name, and like round robin your requests through there and do load balancing. And we said, like, great, that worked well for us. But then when we looked back 6 months ago when we did that, is when we started SYN flooding ourselves. And actually, at this point, we were still pretty confused because we read the gRPC code and figured out like how it was actually building stuff behind the scenes. So gRPC has an abstraction called a channel, which represents connections to a connection to an upstream server. And in either case, gRPC would end up setting up its channels like this. So it would have one channel per IP address. And the only thing that we actually changed here was where the DNS resolution was taking place. So it used to happen in this blue application code box, and we moved it into the green gRPC box. But like, it should have been identical. We were super confused. And we read the code, and we realized that pick first and round robin actually have a very subtle difference, and it's the way that they handle connection failures. So in pick first load balancing, it does basically like lazy reconnection. If it loses a connection to an upstream, it will only try to do that on your request path. So a request will come in, and it will say, hey, I don't have a connection there, and I'm going to block the request until I reconnect. And we actually had a bunch of issues there, like long before this incident, because our reconnection was not aggressive enough. And so we were timing out requests before we could reconnect. And so we changed a setting, which is called max reconnect backoff MS, and set it to 300 milliseconds. And this said, you should wait at most 300 milliseconds when you're trying to reconnect. And this made total sense when we were doing it in the request path because we didn't want to block the request for very long. But in round-robin load balancing, the way that this works is that gRPC tries to be a lot smarter, and it tries to do that load balancing in the background so that when your request comes in, you already have the connection there. You don't need to block it to reestablish the connection. But what this meant is that we had very, very, very aggressive reconnection settings, and it was all trying to happen in the background to all the upstreams all at once. And this sort of explained where our SYN flood was coming from, because we had thousands of alerting engine pods, and they were all trying to reconnect every 300 millisecond to each metric service pod. And here we're seeing like tens of thousands of SYNs per second. So there's our SYN flood. And very surprisingly here, the fix for this just ended up being to delete these overrides that we set on the reconnection settings in gRPC. Instead of overriding them to be like in hundreds of milliseconds, we deleted them and used the default values, which is like a few seconds for each of these, like to wait for how long you should reconnect. And finally, this was several months after we started. We were able to do a rolling restart, and we didn't see errors happening.
So debugging this incident was really long and painful, but we ended up learning a lot from it. And we hope you learned something as well. And sometimes it really isn't DNS. We know it's super rare, but all the initial symptoms can tell us that it's DNS. And people kept telling us that it was DNS, but it was not DNS. So we use some really powerful abstractions like cloud networking, Kubernetes networking. And these abstractions are kind of magical in a way. And most of the time, they work really, really well. But on those few occasions when they don't work, we need to be ready to dive deep and understand those abstractions and spend a lot of time. We also realize that GRPC setup can be quite complex, as you can see. And making subtle changes can end up being very dangerous. And low-level instrumentation like ENA metrics and VPC flow logs can prove to be extremely useful during complex incidents. And we're only two of us on stage here, but this was a complex team effort that took us several months to get to the bottom of. So special thanks to Laurent, Wendell, Matt, and AF for all the help with the incident. And we also have a blog post that gets into this incident in a lot more detail. So if you're interested, do check it out. And if you're interested in working on weird and fun networking issues like this, we're hiring. So you can check out our careers page. And you can also reach out to us on Twitter or email. Thank you.